All right, so going through the rest of the video, or the rest of the study guide, hopefully this will be able to put both pages on one. So number 6, two variables are inversely proportional to each other. Okay, if one variable value increases, what happens to the second variable value? Well, inversely means opposite. Okay, so if we're going up with one, we need to go down with the other. So if it increases, the other one's going to decrease. Okay, if they're directly proportional, and we have one increase directly, think same. Okay, they're going the same direction. So if one increases, the second will increase. Okay, so for pressure and volume, which proportion relationship, inversely or directly, is correct? And one way to help with that is the PTV stick. Okay, so constant for pressure and volume, one goes up, the other goes down. That's opposite, so it has to be inversely. Okay, temperature and volume, which proportion relationship, inversely or directly, is correct? All right, so pressure stays the same, increase one, and the other increases as well. So that's direct relationship. So how do you decide when to use the simple gas law equations versus the ideal gas law to solve a problem? Well, as kind of mentioned a little bit before, the ideal gas law has to be under certain conditions. Okay, that's the reason there's the word ideal. It needs to be specific ideal conditions. Simple gas laws involve changing conditions, because that's where you get that P1, V1, T1, P2, V2, T2. So that's the changing one. And so, if you have changing conditions, so those changing variables, that's when you're going to use the simple gas law equations. Boyle's law, Charles' law, combined gas law. And then the ideal gas law is certain conditions, or basically when you just have those set gas, the set pressure, set volume, set temperature, and set moles. Because you're not changing them, because then it would no longer be ideal conditions. So we kind of use this a little bit. So we did this during the ideal gas law problem. So again, liters for the units of the ideal gas law constant, liters times atmosphere over moles times Kelvin. And if you're unsure, just remember the equation and isolate the R. Okay, you're going to get PV over NT, pressure, atmosphere, volume, liter, and moles, K for the temperature. Okay, so it's the same thing. All right, under what conditions would you not use the ideal gas law equation, and why? So kind of mentioned that above. So for ideal gas law, they have to be ideal. So ideal means high temperature, low pressure. And that's where I said that STP, standard temperature and pressure. So cannot use the ideal gas law with low temperatures and high pressures. Okay, so low temps and high pressures. Okay, so you just need to be careful, with that. Because the low temperature, there's less gas molecules in a certain volume. And then if you have high pressure, that's also going to affect the condition and the volume. So you wouldn't be able to. So it doesn't really matter the volume, but we do need low temp and high pressures. Okay, because that low temp, there's less gas molecules. So it's not going to be as accurate. And then having a higher temp, the pressure, having more gas molecules can mean a high, generally kind of a higher pressure, but we just don't want too high. So 13, a flexible container is kept at a constant temperature. How can the pressure be increased? So if you think about a flexible container, like a Tupperware container, constant temperature, if we increase the pressure, we need to decrease the volume. So you squeeze the container. And that's going to decrease the volume and increase the pressure because there's less area for those molecules to go. So decrease volume, squeeze container. That's going to help. All right, a container has a particular number of molecules of a gas and the temperature is decreased. What happens to the pressure? Temperature decreased, and we want to know what happens to the pressure. So volume stays the same because it's got the particular number of molecules. There's Avogadro's law right there. Ready? We're going to decrease the temp, so the pressure decreases as well. Okay. And that's why really that PTV stick can really come in handy. And honestly, just writing it on your, write it down at the bottom. You don't have to give it a ton of space, but just be able to, that you can cover one and turn it. Okay, and that's really going to help. All right, so let's do the last page. There we go. Had to make sure that was the right one. So 15. If air is in a flexible container, what happens to pressure and volume when adding air? And which gas law can explain this? Well, if pressure and volume means Boyle's law. So if the volume decreases, pressure is going to increase. Okay, because remember the PTV. Pressure and volume is Boyle's law. Okay, I guess I need to make that a little larger. Okay, PTV, you increase one, you decrease the other. That's that inverse relationship. Okay, how will the volume of flexible container of air change with temperature? And which gas law can explain this? Well, this is Charles's law because we're looking at volume and temperature. Okay, so again, looking at that PTV, goes up, goes up. Okay, so if the temperature increases, so will the volume. And if you think of a Tupperware container. I don't know if you've ever put something hot in a Tupperware container and then put the lid on, but you can kind of see the lid start to like dome up. Okay, where normally it's just the flat. And if it's hot, that's because the volume is increasing, because the temperature is increasing. Same thing if the temperature decreases, like let's say you put it in the fridge, okay, it's going to come back down to its flat and even go down the more you close it in. And that's kind of also where you get like, when you vacuum seal something as well, because that's going to help with that freezer. If you freeze something. So again, Charles's law, and you can use the PTV, goes up, or think of the Tupperware container and putting in hot liquid and then putting in the refrigerator. How does the pressure of the air change as you decrease the temperature of the air in a balloon? Here's the PTV stick. Decrease one, you decrease the other. So if you decrease the temperature, you're going to decrease the pressure. Okay. It's also why in cold temperatures, balloons are not going to either inflate as easily, or they're just going to kind of start to shrink. So 2 rigid containers. So there's so that same number of molecules. We can't squeeze it or do anything like that. We have a large container and a small container. So this is referring to the volume. So this is volume, volume. So which container has the higher pressure? Again, this is pressure and volume, so this is Boyle's law. And remember, pressure and volume are inversely related. So if one's up, the other's down. And so the higher pressure is going to be the lower volume. So it's actually the smaller container. And if you think about it, that makes sense, because if you have a small container, there's less area for the molecules, because there's the same number of molecules, there's less area for the molecules to go. So they're going to keep going faster, and it's more likely to bounce off. Okay, and that's what creates pressure, which actually goes to our next question. Based on the kinetic molecule theory, describe what pressure is. And so basically gas particles, gas molecules are in constant motion. So they are constantly moving and they're bouncing off each other. Every time a gas particle hits something, either another particle or, the end of the wall of the container, it's going to exert force. And so that's what pressure is. That pressure is that force that the gas particles create. So hopefully that helps. I have it written down. But pressure is the force created by the gas particles bouncing off. Okay. What does a barometer measure? Atmospheric pressure. Okay. Think pressure. Remember, we love it in atmospheres. Okay, so that's just the atmospheric pressure. So it actually goes in ATMs. It's actually the unit. All right, so, and again, I have these written down that I'll send you a picture of so that you can, visualize it a little bit more. All right, so what causes liquid to go up in a straw when you use it to drink? So it's actually interesting. When you put your mouth around a straw, it creates pressure in your mouth and the top of the straw. Okay, so there's pressure in the, excuse me, in your mouth, just in the beginning of your mouth by the straw and the very top of the straw. The air outside of the straw basically pushes down on the drink, which forces the liquid up into the straw. Okay, so again, that's kind of thinking Boyle's law. Okay, the pressure and volume. Okay, pressure increases on the drink. The volume is going to decrease in the drink because it's going up in the straw. Okay, and a smaller volume in the straw is also more pressure. So that's kind of going up. All right, use the ideal gas law to find the number of moles in a 500 milliliter container. Doesn't say but that's okay. of some gas at 18 degrees Celsius and 600 millimeters mercury. So here's kind of where you have to remember specific units, because you have that R. Okay, that PV equals nRT, and that has to be in the specific units. So this needs to be in liters. So here we go. Here's our decimal point. Milliliters to liters, that's 3 jumps. And we're going from smaller to larger. So to the left, 1, 2, 3. So that is 0.5 liters. Okay. Also remember, there was no decimal point here or here. So our significant figure is 1. Okay, so 18 degrees Celsius, we need to convert to Kelvin, so that's 291 Kelvin. And 600 millimeters mercury, so we're going to divide that by 760 millimeters mercury, because that's going to be atmospheres, okay, to convert it to atmospheres, and we get 0.789 atmospheres. Okay. So now we're just going to plug in. Okay, so we're going to have our 0.789 atmospheres times 0.5 liters is equal to, we want to find the number of moles. R is our constant, 8205 liters atmosphere over moles Kelvin. And then times temperature, which is 291 Kelvin. Okay. When we isolate the N, we're going to get 0.08205 liters atmosphere over moles times Kelvin. Okay. times 291 Kelvin. And, oh, I'm sorry. I'm going to actually cross that out because that's actually going to be on the bottom. And I apologize. I'm going to rewrite this for you. So sorry about that. All right, so we're just going to, we'll plug this in. 789 atmospheres. I'll rewrite this for you. Is equal to N, 0.0 times R, moles Kelvin, times 291 Kelvin. Okay, so now we're going to isolate the N, and we're going to take this and bring it over here. So we actually have 0.789 atmospheres. I just flopped them. 0.5 liters over, and now this is going to be on the bottom, 0.08205 liters atmospheres, which is on the bottom now, and actually the moles times Kelvin gets flipped up. I'm just going to do that so that you can see that and this just stays on the bottom. Okay, because it doesn't matter where we put them, because it's multiplication. And then 291 Kelvin. So you can see here, moles is going to be what we're left with. Kelvin goes away. Liters goes away. Atmospheres goes away. So when we plug it in, let's see, we get 0.0165 moles. We need, I believe, one significant figures, 0.02 moles. Okay. All right, finally, Dalton's partial pressure is probably my favorite gas law, because it's, it's simple and it works. But there's a little added trick to this. So a diverse gas cylinder is made up of nitrogen, oxygen, and other trace gases. Which is definitely true. You can't just breathe in oxygen if you're diving. It's kind of a mix because that's the air we breathe. So 78% is nitrogen, 1% is just the trace gases. Total pressure is 2,640 psi. Okay. So basically, we want to find what is the pressure of oxygen, not the percent. Okay. So again, that's just important for reading. So so we need the pressures of nitrogen and the other gases. We have the total. So what we're going to do is just take 78% of 2,640. Okay. So to do this, 0.78 times 40. Okay. And we get, sorry, I wrote this down earlier, 2,059.2 psi of nitrogen. Okay. Only 1% for the other gases of 2,640. So we're going to go 0.01, because we need to just put it into decimal form, times 2,640. And that's just 26.4 psi of, the trace elements. Okay, I'm going to grab another card so that there's room. Now, here's the easy part. All right, so, P total is equal to P1 plus P2 plus P3 and then dot. Well, there's only 3 numbers here, so we only need these 3. Okay, so we actually know our P total. Doesn't really matter if we have the units here. I mean, it's just keeping consistent. So P1, again, it's just adding 2. So, let's say we're solving for P1. Doesn't really matter. Let's say that's our oxygen. And we have 2,059.2 psi. That's of the nitrogen plus 26.4 psi of the other. Okay, add these and just subtract it. Okay, so 2,640 240 minus the sum, 259.2 plus 261. Okay. And so our P1, which is oxygen, you know, again, it could have been P2 or P3, doesn't matter because they're interchangeable for this one, is 554.4 psi of oxygen. Now I believe it was, I don't know if she'll want significant figures for this. That's only one significant figure. I mean, you could do 600 if you're just rounding up. Again, I'm not sure if she's going to want significant figures. Again, this is also just percentages. So, you know, I would maybe verify with her on the test for that, if she wants those significant figures, and to kind of just remember that the placeholders are not going to count. All right, so really like this problem. This is nice and easy. Helium and argon in a balloon exerts a pressure of 0.80 atmospheres and 0.97 atmospheres. What is the total pressure? All it is 0.80 atmospheres plus 0.97 atmospheres, and that's just our total. So it's 1.8. We could see that there's two significant figures. So right here, and it's in atmospheres because that's what we're keeping. It's not atmosphere squared because this is addition. Okay, it's not multiplication. If it was multiplication, then it'd be atmosphere squared. And that's all. That's really all it is. I know it seems like a lot, but condense it and remember that they're all interconnected. You know, just to remind you know, to help remind yourself. And again, for those units, if you're unsure which one needs the set units, remember all the set units and just go with those. Okay, and that's okay. So like even Boyle's Law, if you had 2 milliliters and you want to convert it to liters, that's fine. Just make sure you include your units. I would see a lot of test answers from past students who didn't include the units, and so I had no idea. Even if the work was right, you know, it still, you have to include the units, so they wouldn't get full credit for that. So that's just something to remember. Remember your PTV, and again, you know, the covering and going up and down. I'll send these pictures, and if you have any questions, you know, please feel free to text me. Calling is a little tough. I can try to answer, but if I'm at work, it's a little difficult, just because I'm at a hospital. But I do work night shift, so, you know, if you're late night studying, I'm awake. So, again, good luck on your test. If you need anything, please let me know. And I hope you do well on both your golf tournament and your test.